Alright, so we just covered the stream's velocity and discharge and what type of factors would influence this too. Now we're going to go ahead and cover the work of the running water as an erosional, transport, and depositional agent. So streams are Earth's most important erosional agents. Not only do they have the ability to cut down and also to widen their channels, but they also have the ability to transport enormous quantities of sediments that are delivered to them by the overland flow, also by mass wasting events or by groundwater. So all of these transported sediments are later deposited to make many landforms. So overall, streams are very, very important landform makers. So let's first look at the stream erosion. So as we saw in Chapter 6, the erosion of particles starts from the work of raindrops and only continues since that moment. From the time that the flow is confined in a channel, the erosional power of a stream is related to its slope and to its discharge. The rate of erosion is also highly dependent on the relative resistance of the bank and the bed materials. So, in general, channels composed of unconsolidated material are more easy to erode than channels that cut into bedrock. Okay, so bedrock is completely consolidated material versus the unconsolidated material through which some channels run. Streams will typically cut channels into bedrock through three main processes. Those processes being quarrying, abrasion, and corrosion. So let's go through each of them. Quarrying involves the removal of blocks from the bed of the stream channel. From the bed of the stream channel or from the sides. So this process is typically aided by the fracturing and the weathering that occurs prior to the quarrying, so prior to that removal. And this is so that the blocks can easily be taken away. So fracturing and weathering, which I guess are what fracturing is, a type of weathering, will aid in the quarrying erosive power. The second process that we have for erosion is called abrasion. It's probably the more common one in streams. So abrasion happens when the bed and the banks of the bedrock channel are constantly being bombarded by particles that are carried into the flow. So abrasion will also cause the particles that have been bombarded to kind of smooth out as they scrap and they rub and they bump into the channel bed and the banks. So they cause these kind of shapes that you're seeing within this channel. They call this kind of pools that are very smooth and round. And it will also typically result in the reduction of size of the sediments that are transported by the streams. So the particles that are responsible for the bombardment, if you think about it, tend to also be reduced in size, and they also tend to be smoothed out as they have been hitting the bed and the banks of the channel. So overall abrasion is responsible for causing the cobbles, that are the parts that have been bombarded, and also responsible of causing the potholes, which are these areas that have been bombarded and are kind of depressions within the channel's bedrock. So corrosion is the third erosional process that we have, and it is an erosive process in which the rock will gradually dissolve by the flowing water. This is very typical and common, I guess, in soluble rocks such as limestone, and it can happen also in areas where streams flow through gypsum or halite, which is not very common, but it can happen in those areas as well. Okay, so all streams, regardless of their size, will transport some weathered rock material. They will also sort the solid sediments as they get transported because the finer and lighter material is carried more easily than the larger and heavier particles. So There are three main ways in which streams will transport their load of sediment. The first one is in solution as the sediment being dissolved load. The second way is through suspension as the sediment being suspended load. And then the third way is by sliding, skipping, or rolling along the bottom of the bed and making the sediment the bed load. So most of the dissolved load is brought to a stream by the groundwater and it is dispersed throughout the flow. So as the water percolates through the ground when it precipitates, it acquires soluble soil compounds that will later go down all the way to the groundwater as it infiltrates. Then this groundwater will seep through different pores and cracks in the bedrock and will dissolve any of the additional mineral matter that it flows through. So much of this matter finds its way back into streams in a process that we will be looking at in the next chapter, chapter 14. So basically, all of these weathered material that is dissolved within the solution will flow back into the stream and it will be carried as dissolved load. So there's basically no effect from the velocity of the stream flow in its ability to carry the dissolved load. The material that is within the solution will simply go wherever the flow goes. Usually, streams will transport the greatest amount of sediment as suspended load. So this type of load is what gives the muddy kind of appearance to streams that have, like the Amazon River or the Mississippi River, that muddy look. So these sediments tend to be of clay and silt size, which means they're small enough to be carried by water that has relatively high energy, but not incredibly high. And so this type of sediment tends to flow throughout the whole stream. So starting from the headwaters to the trunk streams, all the way to the mouth of the streams for the most part. So this material, which again is of clay and silt size for the most part, it also increases if the stage of the stream increases. So typically, grains that are more flat tend to stay in suspension longer than any round grains. So those grains that are a little bit flatter, if you can think about it, will have a greater resistance to the sinking than will the round grains. And so they tend to be suspended a little bit longer and flow further downstream. Coarser material, which will include coarse sands, gravels, and sometimes even boulders, will typically move along the bed of the channel as bed load. So the particles that make up the bed load will move by either rolling, sliding, or saltating. So sediment that moves by saltation is sediment that takes leaps, so that appears to kind of jump or skip along the stream bed. So this occurs by other particles that are being propelled upwards and then collide against the bed of the stream. And so you have these propelled particles be lifted in the current and then carried downstream short distances until the gravity pulls them back to the bed of that stream. So some particles, however, are too large to saltate or leap, so they will typically just roll or slide at the bed of the stream depending on their shape. So if they're a little bit more round, they will typically roll, but if they're a little bit more elongated, they are more likely to slide. So bed load will move a lot slower than suspended load for the most part, and it tends to be a little bit more localized. So a few studies have said that in some kind of glacially related sediments in Nordic regions, the suspended load will flow out of the drainage basin within days. However, the bed load will flow out of the drainage basin within years, if any, or to decades or even centuries of years. So it's a lot slower movement than the suspended load. So in the video here, you will see a representation of how particles will actually saltate. So this is just a recreation in the lab, but overall gives us a pretty clear idea of how saltation occurs. So you see those particles kind of being thrown upwards, and then with the current and by the force of gravity will eventually sink down, and by their action of collision propel more particles upwards into the current. A stream's ability to carry solid particles is described by using two different criteria. One is the capacity, and the second thing is the competence. So the capacity is the maximum load of solid particles that a stream can transport per a given unit of time. So with greater discharge, there's going to be an increase in the capacity of a stream. So larger streams will have a greater capacity to move overall sediment load. Competence, on the other hand, is the stream's ability to transport particles based on the size rather than the quantity of the particles. So in the case of competence, flow velocity is the key factor, not so much discharge, although it is related. So if a flow velocity is great, then there will be an increase in the competence that the stream will have. A stream competence increases proportionately to the square of its velocity, meaning that if the velocity of a stream doubles, then the competence will be 4 times as great as it used to be. Or if the velocity triples, then the force that the stream will have to move this large size material is 9 times as great as it used to be. By looking at the erosion and the transport of sediment by the streams, it should be pretty clear why it is that in large floods there tends to be an associated time of peak erosion and peak transportation of the sediments. Alright, deposition will occur whenever a stream slows, so causing a reduction in the competence and the energy of the stream. In other words, particles are usually deposited when the flow velocity is less than the settling velocity of the solid sediments. The graph that you see on the bottom left of the slide is very good at exemplifying the 3 main zones of a stream based on the flow velocity and on the particle size of the sediment that is being transported. So particles are typically being eroded when there's a high flow velocity, and it's somewhat dependent on the size of those particles. So particles that are kind of sand size tend to be removed at relatively low velocities, but particles that are small or large tend to need a higher flow velocity for them to be eroded. Particles tend to be transported under a kind of medium flow velocity for the most part, but are still pretty dependent on size. So particles that are smaller in size don't need as great of flow velocity to be transported, but particles that are very large tend to need a very high velocity in order for them to be transported. And then finally, particles tend to be deposited under lower flow velocities. So for the most part, it is very dependent on size, but smaller particles tend to be deposited at low flow velocities, and larger particles tend to be deposited even at high flow velocities because they need a lot of velocity in order for them to be either transported or eroded overall. So typically when the streams slow down, particles will begin to settle. The largest ones will settle first, and then the finer ones. So there will be a grading or a sorting in the size sequence that you're seeing as the particles get deposited. The sediments the sediments that are deposited by the streams are called alluvium, as you're seeing up here. And so the alluvial deposits are typically deposited on stream beds, on the sides of the channel at times, so as bars, on the floodplain, or at the mouth of streams. And we'll look at some depositional environments as we cover stream channels and as we cover some depositional landforms later in the lecture.